Bounds on the frugality ratio. The example we saw earlier shows that the VCG mechanism does not in general have small frugality ratio. There is, however, one class of such systems for which VCG is known to have optimal frugality ratio equal to 1 and is given in the following theorem. See exercise 13.12. Theorem 13.53. VCG has frugality ratio 1 if and only if the feasible sets of the set systems are the basis of a matroid. On the other hand, for path auctions, say when there are two parallel paths, each consisting of many agents, VCG can have frugality ratio omega of n. The following lower bound shows that this bad case is not unique to the VCG mechanism. Theorem 13.54. Consider the path auction problem on a graph G consisting of two vertex disjoint ST paths, P and P prime, where the size of P is equal to n. The size of P is the number of agencies on the path P, and the size of P prime equals to n prime. Then, any truthful mechanism for buying a path in this graph has frugality ratio at least omega of the square root of n times n prime. Proof. Define v to the pi to be the vector of private values for agents in P in which hi on P has cost 1 over square root of n. So its value is vi equals to minus 1 over square root of n, and all the rest of the agencies in P have cost 0. Similarly, let v to the p prime j be the vector of private values for agents in P prime, in which age j on P has cost 1 over the square root of n prime, and all the rest of the agencies have cost 0. Let M be an arbitrary deterministic truthful path auction applied to this graph. Define a bipartite graph G prime with a node for each edge in G and the directed agencies defined as follows. There is an edge from node I corresponding to edge I in P to node J corresponding to edge J in P prime, respectively, and edge from J to I. If when running M on bit vector V to the Pi, V to the P prime J, path P prime wins, respectively P wins. Since there are n times n prime directed agencies in this graph, there must be either a node I in P with at least n prime over 2 outgoing agencies or a node J in P prime with at least n over 2 outgoing agencies. In the former case, observe that by the monotonicity of any truthful mechanism, P prime must still win even if all agencies in P prime beat 0 and the payments to each of the relevant agencies equal their threshold bit, which is at least 1 over square root of n prime. Thus, the total payments are at least the square root of n prime over 2. Since, in this case, the cheapest Nash equilibrium is 1 over square root of n, we obtain the desired lower bound. The analysis for the second case proceeds mutatis mutandis. The previous lower bound can be generalized to randomized mechanisms. An immediate corollary of this lower bound is that any truthful mechanism has frugality ratio n on a graph consisting of two vertex disjoint paths of length n. Thus, for this graph, VCG achieves the optimal frugality ratio. On the other hand, if n prime is equal to 1, the above lower bound on the frugality ratio of any mechanism is square root of n. However, for the case of two parallel paths, one of length 1 and one of length n, VCG has a frugality ratio of n. The worst case is when the long path wins. This raises the question of whether or not there is a better truthful mechanism for this graph. The answer to this question is yes. The principle is fairly simple. If a large set is chosen as the winner, each of its elements will have to be paid a certain amount depending on the other agent's bids. Hence, to avoid overpayment, a mechanism should, within reason, give a preference to smaller sets. Thus, rather than choosing the cheapest feasible set, i.e. the social welfare maximizing allocation, one could consider weighing the cost of a feasible set by weights that capture the relative sizes of those sets compared to other sets. To obtain a near optimal mechanism for path auctions, the precise magnitude of these weights should be chosen to balance the worst-case frugality ratio over all potential combinations of winning sets. To illustrate this, let us return to the graph consisting of two vertex disjoint paths. We can balance the worst-case frugality ratio by choosing the path that minimizes square root of the size of P times C of P, where C of P is the cost of the path P, i.e. C of P is equals to minus times the summations of Vi summing for all index I in P. Notice that this mechanism uses a monotone allocation rule and hence is truthful. In this case, if the two paths are P and P prime, and say P is chosen, the payment to each edge on P will be upper bounded by the square root of the size of P prime times C of P prime over the square root of the size of P. This is because the threshold bid and hence the payment to an HE on P is the largest value they could bid and still win. Thus, the total payments are the size of P times the square root of the size of P prime times C of P prime over the square root of the size of P, which is less than equals to, by simplification, the square root of the size of P times the size of P prime times C of P prime. Since C of P prime is a lower bound on the cheapest Nash of N, the ratio of payments to cheapest Nash is upper bounded by the square root of the size of P and times the size of P prime. The same bound holds when P prime is the selected path, resulting in a frugality ratio matching the lower bound to within a constant factor. These ideas can be generalized to get a mechanism whose frugality ratio is within a constant factor of optimal for any path auction problem, as well as some other classes of hiring a team problems. For most set systems, however, the design of a truthful mechanism with optimal or near optimal frugality ratio is open.